Exercise 27. A winch at the top of a 12-meter building pulls a pipe of the same length to a vertical position. So in this exercise, this is the pipe. It was lying on the floor and connected to the roof of this building by a rope. And as the rope is pulled in, the pipe gradually raises until eventually it will be vertical along the building. The winch pulls in rope at a rate of negative 0.2 meters per second. Find the rate of vertical change and the rate of horizontal change at the end of the pipe when y equals 6. So because this rope here is getting shorter, the rate of change of the length of the rope is a negative number, negative 0.2. So let's see what we can do with this exercise. I like this exercise a lot. It's complex. You need to gather many informations in many places. It's virtually impossible to have a complete idea of how to solve it before you jump into it. And there's many times where you figure out that you need more information. So how can you make more information with the information you already have? It's really challenging, but excellent exercise. So here's an image of our situation with the building being 12 meters high. This is the pole, it's also 12 meters, and the rope that is pulling in. So this is a triangle, an isosceles triangle. I don't know if that's going to be useful right now, but when I see isosceles triangle, I often think of dividing them in two because it creates right triangles. Right triangles are very useful. We know SOHCAHTOA, we know the Pythagorean theorem, so maybe that's going to be something we're going to want to do. The question in this exercise is to find out how this point here, what the rate of change of this point is horizontally and vertically. So how much is it moving horizontally and how much is it moving vertically? So to warm up, we can wonder whether these two numbers are going to be positive or negative. We can remember the x and y axis. So the answer is that dx dt should be a negative number because as the winch pulls rope in, this point is going this way, so the x value is decreasing until the x value will be 0 if the origin was here. On the other hand, dy dt is positive because this point is rising. It's going to get higher and higher as it reaches the top of the building. So this should be less than 0, and this should be greater than 0. So what can we do? Since we have x and y that we need to find, we probably want to show them somewhere on the graph and see if we can find a connection between them. So here, probably the best idea is this one, where we have x and y, and I have a right triangle there with a hypotenuse of 12. So that allows me to set up an equation, so I'm extremely happy with that. X squared plus y squared equals 12 squared. And in fact, if I take the derivative, implicit differentiation, 2x times dx dt plus 2y times dy dt is equal to 0, because 12 squared is a constant. What I really like about this is that I managed to make dx dt and dy dt show up. That's an excellent result. Do I know x? No, I don't. Do I know y? Yes, I think I do. Let's check again. I think it was said that I'm looking for the vertical rate of change of the pipe moving horizontally and vertically when y equals 6. Excellent. So y equals 6. Let me add it to the list of things that I know. So I can actually use this one here to find out the value of x. So x squared plus 6 squared equals 12 squared. X squared, 144 minus 36 is 108, so x is root 108. Very good information. Let me just plug it in. 2 root 108 dx dt plus 2 times 6 dy dt equals 0. I don't know dx dt and dy dt. In fact, these are the two questions in this exercise, so I need to find something else now because I'm stuck. And clearly, I haven't used the fact that ds dt is negative 0.2. That's a key information. It tells us how quickly this point is rising since it's being pulled along the rope. So how can I do that? Well, here's an idea. Maybe I'm going to look at this triangle. I like this triangle because it involves S. And that's definitely a good thing, since after I differentiate S, it's going to make ds dt show up. So in this right triangle, that's still x. What about this height here? Well, it's 12 minus y. So that's perfect. I can set up a new equation using the Pythagorean theorem. X squared plus 12 minus y squared equals s squared. If I take the derivative, 2x times dx dt plus 2 times 12 minus y times negative 1. That's the inside derivative, the derivative of 12 minus y times dy dt equals 2s times ds dt. Here 12 squared was a number, so the derivative was 0. S squared is not a constant number because s is changing. This length is getting shorter and shorter as the rope is being pulled in, so therefore the derivative is not 0, it's 2s times ds dt. Let's have a quick look at what I know here and what I don't know. I know x, I know y, I know ds dt. So I don't know dx dt, I don't know dy dt, and I don't know s. However, I can find s, because from this here, I can recycle this equation, and now I can set it up. X is the square root of 108, plus y is equal to 6, so 12 minus 6 is 6 squared, and that has to be equal to s squared. 108 plus 36 equals s squared. So 108 plus 36 is 144. S equals 12. Wait, 12? That's the number we have everywhere. Is that a coincidence? Let's see. We now can make a new sketch. This is 12. It's a little disturbing that there's 12s everywhere. We're not quite sure if it's always 12, or I don't know. This is actually what the image looked like. So the sketch in the textbook was not to scale, and it was kind of designed to throw us off. It looked like the rope was almost at its end. Actually, it's pretty far. When you think about it, this is an equilateral triangle. We knew that y was equal to 6, so that meant there was 6 remaining to reach the top of the building vertically. So it actually makes sense. Maybe we could have guessed that from the beginning, but we didn't. So anyway, here we are. Now we know that s equals 12, so I have plenty of information that I can now find out. Indeed, this equation, let me give it a name, equation 1, has two unknowns, dx dt and dy dt. This equation here will only have two unknowns as well, dx dt and dy dt, so now I know I'm going to be able to solve this entire problem. So 2 root 108 dx dt plus, oh, it's going to be minus 12 dy dt equals 24 times negative 0.2. 24 times negative 0.2. If it was 24 times 2, it would be 48, so negative 4.8. Very good. I'm going to call this equation 2, and now I'm only going to work on with these two equations. From equation 1, I'm going to solve for maybe for dx dt. Dx dt equals, so the 2's cancelled out, minus dy dt, and I have 6 of them divided by, so minus 6 over root 108 dy dt. I can plug this in equation 2. 2 times root 108 times negative 6 over root 108 dy dt minus 12 dy dt equals negative 4.8. Okay, I'm very happy that these square roots cancel out. Minus 12 dy dt minus 12 dy dt, I get negative 24 dy dt equals negative 4.8. So dy dt equals 4.8 over 24, and that is that if it was 48, 1 over 5. And what are the units? Y is in meters, t is in seconds, so 1 over 5 meters per second. We're just seconds away from the answer, from the complete answer. Dx dt is, if I go back here, negative 6 over root 108 over 5, so negative 6 over 5 root 108 meters per second. I bet I could cancel out this a little bit. I can extract a 2, I can extract a 3. Shall we do it? Yeah, maybe, why not? 108 divided by 4 is 27. So I divided by 4, so now it's negative 3. And now here I can still extract 9 from the square root, so it's going to be negative 1 over 5 root 3 meters per second. So this is the final answer to this consequent exercise. As we see, we never used the fact that we can split isosceles triangles in two, but it's a trick we want to remember because sometimes we need to. In the other exercise we do in this section, we have a man 6 feet tall walking at a rate of 5 feet per second away from a light that is 15 feet above the ground. When he is 10 feet from the base of the light, at what rate is the tip of his shadow moving, and at what rate is the length of his shadow changing? So, this exercise is in 2 dimensions, even though you may have observed your shadow when you walk in the night move about. In this exercise, we have to be aware that If this is the lamppost, the man walking walked exactly below it, and he's now walking in a straight line. So I put a 15 because the lamppost is 15 feet tall, and the man is 6 feet tall. So this is it, and the shadow is actually this part here. So the shadow is getting longer as the gentleman is walking further. When we say that x is here, what it actually means is that this length is x, right? So we have questions about how the shadow changes. So there's two ways of approaching this problem. We could either go ahead and say that this length here is something, or we can just talk about this length here. And that's what I'll do. The reason is I called it S for shadow. I kind of prefer to have this because now I'm going to be adding lengths. I'll have X plus S maybe. Whereas if I pick a length for the entire thing, then how do I describe this one? It's going to be whatever this is minus X. So I just prefer, I guess, since I don't really know what this exercise is going to look like yet, I'd rather put two small pieces and add them rather than two long pieces and having to subtract them. So we know how fast the man is walking. He's walking at 5 feet per second, and we know that the questions are about when the man is 10 feet away from the lamppost. However, we can't just put a 10 here. If we put a 10 here, what happens is we have 15, 10, 6, and we can use similar triangles and figure out what this number is, and maybe we will need to. I'm not saying we shouldn't ever do that, but if we start by doing that, we're freezing the situation into one picture. It's a picture, it's not moving anymore. There's no difference between the man walking at 5 feet per second or the man just standing here, right? And the question is a question about movement. It's a question about rates. So it's really important that we keep the x, because we're not studying a picture like we used to do in pre-calculus or algebra 2. We're actually studying a movie. We're looking at how this is developing from one frame to the next. Okay, so how can I express a connection between x, 6, s, and 15, x, s, 6, and 15? I just mentioned it here. We can use similar triangles. So 15 over x plus s is equal to 6 over s. And because I know dx dt, it's quite clear that I'm going to want to take the derivative of something because I have an x, so taking the derivative is going to produce a dx dt. However, I'm not forced to do it right here. If I did it right here, it could actually become pretty complicated. Nothing prevents me from making this a little bit easier by cross-multiplying. 15s equals 6x plus s, so 6x plus 6s. And then I can subtract this 6s, and I get 9s equals 6x. I can divide by 3, 3s equals 2x. This is so much easier to differentiate, right? So you can do it here. Maybe you would do it if it's your first attempt at this question, but actually simplifying the algebra before entering into the calculus world is really, really wise. So implicit differentiation, the derivative of 3s is 3 times ds dt, because we are differentiating in terms of t, not s. What's the derivative of 2x? It's 2 times dx dt, because we are differentiating in terms of t, not in terms of x. Now, dx dt is 5, so I find ds dt equals 2 times 5 over 3. 10 over 3 feet per second. I'm done, I found an answer, but now what answer is it? What I found is how S is changing. So S is the length of the shadow. How fast is the length of the shadow getting bigger? And so let's have a look at the question again. At what rate is the length of the shadow changing? So we actually answered question B first, and that's totally okay because we didn't have a perfect roadmap of this exercise, but we managed to find a connection between X and S, and we managed to find ds dt. So we did some great work, and it's totally fine that we weren't able to find A before B. But now let's look at A a little bit more carefully. At what rate is the tip of his shadow moving? So that means how fast is this point moving this way? And that actually requires us to study how this whole length that I'm now calling y is changing. If I'm studying how fast this point is moving, I'm actually studying how quickly this y length is changing. It's like a rubber band. How fast am I stretching this to the right? So I need to start again, and this time to answer question A, I'm going to actually be looking at what dy dt is. So, same trick. Let me put a B here, and perfect, I can go back here and do A. I'm going to use similar triangles again, but this time I'm going to use 15 over y, because I know dy dt is what I'm interested in, is equal to 6 over, now I have a choice. I can either say 6 over s, or I can say 6 over y minus x. It doesn't really matter which one I do, because when I take the derivative, I will have dx dt, it's here, and I also happen to have ds dt because I solved b before a. Was I solving a first, then I would kind of be bound to write y minus x. But since we solved b first, let's show how convenient it was to solve b before a and write it as 6 over s. Cross multiply 15s equals 6y. I take the derivative 15 times ds dt equals 6 times dy dt, and therefore dy dt equals 15 times 10 over 3 all over 6. What's that? 150 over 18. That's, if I divide by 3, 5, 50 over 6, 25 over 3 feet per second. So that's the final answer for question A. Now, if we look back at the entire question, one thing that's interesting is to realize that we actually never used this information. What it means is that it doesn't matter where the person is, the rate at which the shadow grows and the rate at which the tip of the shadow moves is independent of where the person is. Great. That was the second problem, slightly easier than the first one. And we are going to move on to one last effort in this section full of complex ideas and complex problems. It's about evaporation. As a spherical raindrop falls, it reaches a layer of dry air and begins to evaporate at a rate that is proportional to its surface area. Show that the radius of the raindrop decreases at a constant rate. So we are given, so we have this spherical raindrop, and it gradually becomes smaller as times go by because of evaporation. So the volume of a sphere is 4 over 3 pi r cubed, and we know that the volume is decreasing at a rate that is proportional to the surface area. So dV dt is equal to K times S. That's how you write proportionality in math. The rate of change of the volume is proportional to the surface. So it's proportional to K, and they give us the information that the surface area of a sphere is 4 pi r squared. So that's information we are given, but we are able to actually calculate that using differentiation. dV dt is, if I take the derivative of this, 4 over 3 pi is a constant, and then the derivative of r cubed is 3r squared times dr dt. So this is 4 pi r squared times dr dt. But we know that dV dt is equal to k times 4 pi r squared. So k times 4 pi r squared. And look at that, 4 pi r squared cancels out, and we end up with dr dt equals k, which is exactly what we wanted. The rate of change of the radius is a constant. So here the proof is complete.